Alright, picking up from the last video, we know that this top left number is our mass number, and that's the protons and the neutrons, and then the bottom number is our atomic number. And the atomic number is officially the number of protons, but if the atom is neutral, it will also be the electrons. So looking at this atom, we can tell that it has 6 protons, because the atomic number. We can tell that it has 6 neutrons, because the mass number is protons plus neutrons, and 12 minus 6 is 6. And we can also tell that it has 6 electrons, because there's no charge shown, and that means the protons and the electrons are equal. Alright, for this example, take a minute and pause the video and figure out how many protons, neutrons, and electrons this atom of carbon has. Alright, so coming back, hopefully you found that it had 6 protons, because of the atomic number, 6 electrons, because no charge, and 8 neutrons, because 14 minus 6 is 8. Another example for you to try to figure out the protons, neutrons, and electrons. So pause and do that, and then come back and check. The bottom number, the atomic number is 1, so there's 1 proton. There's no charge, so there must also be 1 electron. And the mass number is only 1, so 1 proton, and the mass number is 1, there must not be any neutrons. Okay, that tricks people a lot. They'll think there's 1 neutron. But hydrogen, the most common form of hydrogen, actually has no neutrons. And so as we get on, on into some more chemistry, we'll look at hydrogen a lot, because when it loses an electron, hydrogen is just a proton. There's nothing else there except a proton if it's H+. Alright, here's another example. This is called deuterium. It's a different form of hydrogen. And you see its mass number is 2. So if you find the protons, neutrons, and electrons there, this form of hydrogen actually does have a neutron. So we saw 2 examples of carbon and 2 examples of hydrogen. They both had the same number of protons and electrons, but their neutrons were different. These are called isotopes. Isotopes have the same number of protons, but different number of neutrons. So their mass number is different, while their atomic number stays the same. It's important to note that isotopes exhibit identical chemical behavior. So the number of neutrons they have does not affect the way they act in a chemical reaction. So H1, hydrogen 1, as well as hydrogen 2, both of those will bond with oxygen to form water. And carbon 14 and carbon 12, the difference in their mass numbers does not affect the way they bond with oxygen to form carbon dioxide. The only difference that number of neutrons makes is in the radioactivity of the substance. It has nothing to do with the way that it carries out chemical reactions. Okay, now we're going to talk about the mass of the atom. So the mass of one carbon-12 atom with its 6 protons and 6 neutrons is exactly 12 atomic mass units. So we assign the number 1 to a proton and 1 to a neutron in carbon-12, so its mass is exactly 12. All other atoms are measured relative to carbon-12. So carbon-12 is the basis for atomic mass unit. That's where the atomic mass unit came from. Again, remember I said this is just a made-up unit. They decided that we're going to say carbon-12 weighs 12 and we'll relate everything else to it. Because atoms are too small to measure in grams, so they had to have another unit, and so this is the unit they decided to use. The atomic mass that's given to you on the periodic table, though, even if you look at carbon, none of these are exact whole numbers. And that's because they are the average of all the isotopes of that element. So remember we saw that there was carbon-12 and carbon-14. So that average on the periodic table is the average of those 2 isotopes. However, Notice that the average for 12 and 14 for carbon is not 13. Okay, so we don't find the average by adding them together and dividing by 2 or 3. Okay, to find the average is going to be a little bit more difficult because there are thousands of hundreds of millions of carbon atoms. Okay, so we're going to have to look at percentages. But the average mass of any large number of atoms of a given element is always the same. So as long as I have a sample of carbon that's large enough, the average mass will always be the same as it is on the periodic table. So how do we figure out the mass of an atom? Okay, this is a really good question because we cannot put an atom on the scale and weigh it. And when we have a bunch of atoms, like a bunch of carbon, it's always going to be a mix of the different isotopes. So how are we going to figure out how much carbon-12 and carbon-14 weigh? Or how are we going to figure out how much sodium-22 and sodium-23 weigh exactly? Or how do we even know that there's sodium-22 and 23 if we can't weigh an individual atom? We use a process called mass spectrometry. And this is used to compare the masses of different isotopes. It takes atoms from a pure sample of an element. So this sample would contain only that element, but it would have different isotopes in it. That sample is then ionized and pushed through a magnetic field. Okay, so you can see here, we're going to put the sample in, and then we're going to shoot it with an electron beam. That electron beam is going to ionize the sample, give it a charge, and then we're going to put it through an accelerator. Okay, that's going to speed it up. So we're basically throwing the atom. As we throw it, it goes through a magnetic field. Now that we've ionized it, it's now positive. So when it comes through the magnetic field, it's going to turn toward the negative side. But notice this, they don't turn the same amount. They both are turning, but they're not turning the same amount. Okay? Think of, a good analogy is if, sorry, I decided to pause and then come back and actually show you this analogy and try instead of trying to explain it. So we're going to watch this video or a little piece of it, and you can see here how a mass spectrometer works. So this is an analogy, okay? If we have 3 different masses, like you see here, and we don't apply that magnetic field, and we just threw them, okay, they would all go straight like you see there. Now we're going to use the blow dryer, which is acting like the magnetic field. It's going to move all 3 of them. But notice that the last one moved a lot less than the golf ball. So the one with the least mass is able to be turned more by that magnetic field. And the heavier one is going to turn less. Okay, so that's the key right there. Let me see if I can go back in the video and you can jot down. This is the key to mass spectrometer. The ball with the greatest mass is deflected the least. And the least mass, the smallest one, is deflected the most. And this applies to atoms. So the isotope that's the lightest is going to be turned the most. And then the isotope that's the heaviest would be turned the least. Okay, here's an actual mass spectrometer drawing. And you can see the same parts that we saw earlier. Here we have where our sample's going in. It's going to get turned into a gas, or they're going to shoot it with some electrons, okay, to give it a charge. It's actually going to knock off its electrons, and it's going to give it a positive charge. It's then going to go through the magnet and be deflected. The pink, you can see, turned a good bit. The yellow is not turning as much. And then as they hit that plate, we're detecting where they hit the plate. So that gives us an idea of the mass and how many times they hit the plate. And that gives us an idea of how many atoms there are of that kind in the sample. All right, so back to our note sheet. What you see at the bottom of this next page is the output from this mass spectrometer. So if we have a pure sample of silver, for example, and we vaporized it, that means turned it into a gas. Okay, you can imagine that's going to require a really high temperature, and then inject it into a mass spectrometer. It's going to go through and be ionized and then turned by that magnetic field, and then those silver atoms are going to turn and hit the plate. The 107 atoms are going to be deflected the most, and then the 109 are going to be deflected less. And as they hit that plate, we're going to figure out how much we have. This is going to then be displayed in percentages. So you can see that we have about 51.8% of our sample is silver 107, and then about 48.16% is silver 109. It gives us the mass of 109 is 108.90476. Your mass for each isotope is going to be a little bit different than your mass number. So if the mass number is 109, the mass is not going to be exactly 109, okay, but something really, really close that would round up to 109 or maybe round down depending on the size of the element. They want us to find, though, what is the mass of silver 107 then? If the mass of silver 109 is given as 108.90476. Okay, so how are we going to solve this? All right, here's our setup. So we have the mass of the silver 109 times its percentage, and we change that percentage to a decimal, plus this unknown mass for silver 107, excuse me, this was 109. This unknown for 107 times its percentage, which I got off the mass spectrometer data, is equal to 107.87. Now, where did this number come from? Okay, this is key. This is your average, and this is from the periodic table. Okay, then we're going to multiply those two together. We get this value. We're trying to solve for this 107. We'll then subtract that 52.45 from both sides and get 55.42. Then divide by the 0.5184. That's that percentage, so we change to a decimal. And we find that the average, or excuse me, not the average, but the actual mass for the 107 is 106.9 AMU. The average for all silver is 107.87. Let's think about that number, 107.87. That's between the 109 and the 107, but it's closer to the 107 because the 107 was 51%, and the 109 was only 48%. So your average from the periodic table is going to be closer to the one that is more abundant in nature or has the higher percentage. All right, in this mass spectrometer, we have an unknown element, and it has two isotopes, 35 with the exact mass of 34.969 is about 76%, and then the 37 with the exact mass given there is about 24%. And it wants us to find the average for these and then identify the element. So to find the average, we just can't say, oh, 35 plus 37 divided by 2 is 36, right in the middle. Now the average has got to take these percentages into account. So how do we calculate that? We're going to change these percentages to decimals and multiply them by the mass that they go with. So the 35's exact mass times its percentage, changed to a decimal, plus the 37's exact mass times its percentage, changed to a decimal. And we get 35.45 AMU. Okay, so what element is that? When we look on the table at the mass, not the atomic number, but the mass values on the periodic table, and we identify that that element is chlorine. 35.45 AMU is the atomic mass given for chlorine on the periodic table.